So, welcome to Computational Commutative Algebra problem solving session. And I'm Siddhi Balwambure from IIT Gandhinagar. And today we will discuss problems related to syllabus from week 8. That is problems related to Artinian Rings, graded modules, Hilbert Polynomial, Hilbert Samuel Polynomial, and Artin-Rees Lemma. So, let us start with the first question that we have to check for true or false. And the question is, let R be a ring just a second. Yes, R be a ring without nilpotent elements or nilpotents. Then the Jacobson radical of R is 0. So we have to check whether this is true or false. So we are asked about nilpotent elements. That is, when they are saying nilpotent elements of R, they are talking about nil radical of the ring R and the Jacobson radical of ring R. So nil radical of ring R is intersection of all primes such that P is in spectrum or of R, and this Jacobson radical of R, which is usually denoted as just radical of R, is intersection of all those M such that M belongs to maximal spectrum of R. So spectrum of R is just collection of all primes, and maximal spectrum of R is collection of all maximal primes. So this is the difference. So we can always see that this nil radical will always be contained in the Jacobson radical, right? Because this is intersection over bigger, this is intersection over bigger set than this. Okay, because here, so every maximal element is prime. So this element is already there, and then we are again intersecting with more elements which are just prime elements. So we always have this containment that nil radical is always contained in the Jacobson radical, and nil radical is also defined like this, that it is all those collection of R such that R power n is 0 for some n, and Jacobson radical of R also has such expression where we can say it is collection of all those R in R such that 1 minus RA is unit for all A in R. Okay, so this is the thing. So first of all, we want to find an example where nilpotent element is 0 and Jacobson radical of R is something non-zero. So this we have to like prove it, or we have to find the counter example of it. So any guesses whether this will be true or not? So the answer is no. This statement is not true, because see, if we have a integral domain, local integral domain, so in that, or local domain, in that case, it will always have a maximal ideal, and that maximal ideal will be unique. So when I take intersection of all M such that M in spec R, then it will be just that maximal element M, that unique maximal element of that local ring. Okay, and nil radical of R in that case will be like if there exists some other ideal which is not that maximal ideal, then nil radical will be that thing. So in this case, we have to find an example where nil radical, so ring R is without nilpotent. So nilpotent, so this intersection of R, so according to given condition, nil radical of R is 0, and we want a ring are such that nil red is 0 and Jacobson radical, that is the radical of ring R, is non-zero. Okay. So any cases, so as I said, local rings. So any local ring will work or local domain will work in this case. So for example, let us take R is equal to Z2. So when I write this Z2, here S is this Z minus ideal generated by 2. Okay. So this we know. So collection of all the elements outside a prime element forms a multiplicative set. So this is my multiplicative set Z minus 2, and that's it. And then prime ideals, we know how the prime ideals in localization look like, right? So spec of Z2 is all S inverse P such that P intersection S is empty. Okay. And P belongs to spec Z. Okay. So it is collection of all the prime ideals. I mean S inverse P, where P is such that it does not intersect with that multiplicative set. Because suppose if I have some P such that P intersection S is non-empty, then since every element of S is inverting and there exists one element in P and S both, then that element X belongs to P and X belongs to S will be X into 1 by X, and this will make 1 by 1 belongs to this P, or let me write here Q. No, P was correct actually. Okay, so this will belongs to that required, or this will belong to this S inverse P, and it will make it to a whole ring. So that's why when we take prime ideals in localized ring with respect to that certain multiplicative set S, then the prime ideals are those which do not intersect with that S. Okay, so therefore this is the prime ideal. So spec Z by 2 will be, sorry, spec of this Z localized at ideal 2 will contain only these elements, right? Spec Z2 will be 0 and ideal generated by 2, right? Because every other element, so for example, if I take 3, okay, then ideal generated by 3, will it intersect with this ideal, this element S? So ideal generated by 3, will this intersect this S? Yes, right? Because S is what? It is essentially all odd numbers. Okay. Odd numbers in Z, or odd numbers in Z. I hope you know what I mean by this. It is odd numbers or comma -1 into odd numbers. Let me be explicit. So 3 is there in this ideal, and 3 intersect this S is non-empty, right? Because we are inverting all the elements, all the odd numbers. Okay, so this 3 by 3, and again, for every prime ideal P is odd, which is there in this multiplicative set. Okay, so P intersection S for any prime ideal generated by odd prime will always intersect with this S. Okay, so that's why spec Z2 contains only these two ideals, 0 and 2. Okay, and 0, because 0 is prime ideal here, because we are localizing Z. Z is integral domain, so 0 is anyway prime there, which is not odd number anyway. Just, it's not in S and so on. But maximal M spec, we know for M spec, it is only this ideal 2. So therefore, nil radical of this Z2 is this 0 ideal or just 0 element. But radical of this Z2 is this only ideal generated by 2. Any doubts here? So when I write this, I mean this ideal generated by 2 in this Z2. Or S inverse ideal generated by 2 and so on. I mean, I hope you understand what I mean here. So this is why this statement is false, and you can generate many such examples actually. So for example, this was one example where we know. Other example is this. For other example I can take is this. So let us take kx. Okay, this, ma'am, please explain how ideal generated by 3 intersection S. Okay, so S is collection of all odd primes, right? So S is, so when I have ideal generated by 2, it means it is 0, 2, 4, x 0, 2, 4, 6, 8, and so on. 0, and from the left side it is -2, -4, -6, right? I mean, these are the elements, so multiples of 2. So ideal generated by 2 is just 2z. Everything multiplied by 2z. Okay. Sorry. This is my ideal generated by 2. And S is what? Z minus 2. Z minus this ideal generated by 2 or this 2z. Okay. So it is S will be what then? 1, uh, let me, plus minus 1, plus minus 3, plus minus 5, and so on. All the odd. Is this much clear? Okay, then ideal generated by 3 will contain 3, right? And then 3 intersection, sorry, this 3 also belongs to this S. So ideal generated by 3 intersection S is non-empty. And in that case, this ideal generated by 3, if I take in my ring S, in my ring Z2, then this 1 by 3 is there because we are inverting the elements. And ideal generated by 3, if I take this S inverse ideal generated by 3, 1 by 3 is there because we are inverting odd numbers in short. And this ideal generated by 3 contains 3. Okay, and this will be 1 by 1 in my local ring. And this will blow up the entire this ideal S inverse 3. Okay, so this will be then entire S inverse R. Or yes, S inverse R or S inverse Z2. I mean, this is S inverse Z. Okay, so this is not prime ideal definitely, because when we talk about prime ideal, we need it to be proper ideal. So is that clear now? And this will be true for any ideal generated by prime P, because prime P is odd. And apart from these two, all odd primes are there. And again, that 1 by P will be there. And again, ideal generated by this P odd, S inverse P. This will be 1 by 1 belongs. Then this will 1 by 1 will imply S inverse Z is equal to S inverse this P. I hope this is now not prime ideal. Again, this is not prime ideal. Is this okay now? Mhm. I mean, how we only have these two ideals here. Okay, great. Uh, the other example for this was, and I hope you also know that that's why these are the only two possible ideals, because ideals, so we are in spectrum. So in spectrum of Z, there are only ideal generated by 0 and ideal generated by prime ideals. So we know that 0 is there and 2 is there, and all the other odd primes are going to whole ring. So that's why it's not there in spectrum and so on. So I hope this is clear. And the other example is this example. I mean, you can work this out. It is kx. So power series, formal power series ring, and with k field. Okay, we need K to be filled in this case. Okay, power series ring is formal power series ring is defined for any ring R, but for us to have this example, we need K to be filled. Okay, and in that case, this 0 is prime ideal. So note that once I have integral domain, nil radical will always be 0, because nil radical means was x power n is 0 for some n in n, right? So in that case, x into x n minus 1 is 0, and in that case we have 0 divisor, which does not happen in integral domain. So whenever we work in integral domain, nil radical always becomes 0. So this is integral domain, and this 0 is prime ideal here. And we can note that the ideal, or the only maximal ideal is, or apart from this 0, every, so how to put it? So we know that if element is of this form, a plus a naught plus a1 x plus a2 x square plus and so on, okay, if this is some f, then this f is invertible if, in fact, if and only if this a naught is invertible. Okay, this is the statement which you can prove it. It's a really easy argument. You can just see what is invertible or unit if and only if a naught is invertible in R, or a naught is unit in my K. K or R if I'm working on a ring. So in formal power series ring, if this is in some Rx, not this R, the ring R, then it will be unit only this. So all the ideals which are kind of generate proper ideals in this ring are of this form. X power R are proper ideals in Kx, this formal power series ring. And therefore, once are all the proper ideals of this form, the only prime ideal which will contain these ideals is this. And so only maximal element, maximal ideal of Kx is this ideal generated by these x. And therefore, again, 0 is, we are in integral domain. So nil radical of this Kx is 0, and radical of this Kx is this only ideal generated by x. I hope this much is clear for now. I mean, one example was enough to show that this doesn't happen. But if you have not yet tried this, please do this. This is a good exercise, and also remember that this is local ring always. I mean, if you want examples uh, in your hand, so this is false. Nil radical 0 does not imply that radical will be 0 always. Okay. And so now we are moving to next question. True or false again. And we are asked that the cruel dimension of an infinite product of a field with itself is a 0. Okay. So cruel dimension means it is denoted by dimension of R. So dimension of R is the supremum of all those L, such that there exists a chain of prime ideals in this P0, P1 contained in PL in R. So it is supremum of all those proper chains. Okay. So we have to show that crude dimension of an infinite product of a field is with itself is 0. So what this ring is? So my ring is this K, this product K. So let K be filled, and a ring R is this product I in K. Okay, so it's K copies, I copies of K, where I is index set. Okay, so these are I many copies of K. It. I hope this makes sense to you. What? So let me just write K into K. This is very bad way of writing, but I'm just writing it I times. Just, I mean, this is not very correct, but just to give you a flair, because we are repeating K at every uh, coordinate and so on. So we have to work with this. So, so we have to see the prime ideals in this ring. Okay, so we know that this happens, that if we will use this fact, that if R is equal to product I belongs to Ri is a ring, then uh, the prime ideals of R are of the form Pi, sorry, Pj cross product I not equal to J Ri. It's of the thing where Pj belongs to spec of Rj. Okay, so prime ideals of this ring are of this form. So when we take product of rings, then its prime ideal is only like one of the component is prime ideal, and rest is all the rings which are at that. For example, it will be of the form R1 cross R2 cross I position Pi cross Ri plus 1 and so on. So how to prove this? So we have to prove this because this is not very trivial. So let Ei belongs to R such that, so we are taking those standard coordinates in cross product with such that ith Ei has 1 at ith place and 0 elsewhere. Okay, so let P be a prime ideal. Okay, if P is a prime ideal, then there exists Ej such that Ej does not belongs to P, right? Because P is proper ideal. Because once I have all the Ej's in my ring Ri, then all the elements of Ri are there. I hope you can see that. Ei is of this form 0, 1, so on. And so I have all the components available, I can generate the entire ring. Okay, so P is a prime ideal and hence proper. At least one of these Ej's will not be there. Okay, there exists Ej such that this Ej is not there. Then what we will do? This, then for all I not equal to J, Ej into Ei is 0. Okay, and because the components are different and when we are producting, so everything is of this just I'm giving you an example, into 0, 1, 0 and so on. So which is 0, 0, 0. So once I and j are not equal, this happens, and this belongs to P. P is prime ideal, it contains 0 element. So this imply my since Ej is not there, it means Ei belongs to P, right? And since Ei belongs to P, and this is true for all I not equal to J. So this implies this 0 is there, and this entire ring Ri such that I not equal to J. So this is like R1, R2, Rk. At jth position, I am taking 0 and so on. Again, Rj plus 1 and everything. This is contained in P. I hope you can see this. This is just a way of writing it. I mean, it is like I'm writing if I have R1 cross R2 cross R3, then I'm just writing it as R2 cross product Ri, I not equal to 2, something of this sort. Okay, and these are isomorphic and they doesn't actually uh, make much difference. So this is contained in P. Okay, when I write this, please make sure that what I'm trying to say here. And then we let this map, we take this map pi j from this I product to Rj be this projection map, our normal projection on j component. Then this pi jp is a prime ideal. And why it is a prime ideal? So if I take, suppose xy belongs to pi jp. So this imply x belongs to pi jp or y belongs to pi jp. This imply there exists some, sorry, this imply what? I need to prove that this is prime ideal. So we started with this. So this is there. Some, what, how to write this? Some T1 at j position this is, and this Tj plus 1 and so on. This belongs to my pi jp. And then this, we don't know what this Tj could be 0 very well. That doesn't matter to us, but I can then separate this, right? T1 into x, Tj plus 1, so on, into 1, comma, again at j1, so on. This is in pi jp. So once I have this, since this is in P, this is in P. So I mean, I have this image here, this is image. So for this image, since this is also surjective map, here let me write, this is surjective map. So for this xy in pi jp, there exists some element which I have taken here, and then I'm just splitting it as a multiplication. But P is a prime ideal, which we started. Okay, so it implies this T1 into x comma Tj plus 1 and so on. Either this is in P or this 1 comma 1 up to y, so on. And in both these cases, we have this x belongs to pi jp or y belongs to pi jp. And this implies that this pi jp is prime ideal. And hence this prime ideal P is actually this pi jp cross this pi I not equal to j or ri. I mean, this is what we get. And this is nothing but, in fact, projection. So it is just I not equal to j, ri, I belongs to I. Is this clear? Like how this cross product and how the prime ideals look here? Or anywhere there is doubt. These are some notations which I mean, used here, but I hope you understand the meaning, what it means. So prime ideals of this form, one of the component is prime and rest are zero. But in our case now, in our example, R is product I in I, K field, and M spec of K is equal to spec of K. It's just ideal generated by zero, right? So therefore, the only prime ideas possible here are zero cross product I not equal to J, K. Okay, so ith component zero, rests are non-zero. And this is my only prime ideal possible, right? Because if my prime, the chain of primes is increasing in this kind of situation, then it will be some P2 cross product Pj, I not equal to J, I in I. Something of that sort. In that component, the chain will increase. Okay, no other component will give me prime ideal. Okay, and this is also not in integral domain. So here 0 is also not a prime ideal. So if you are considering this 0, 0, this ideal generated by 0, 0, 0, 0, this is not prime here, not prime, because this into is 0, but none of them is available in ideal 0. So 0 is not prime. So only prime ideal is of this kind, 0 at one of the component, and rest is my the copies of my field K. So and this is my P0. So dimension of my ring R is a 0, as we wanted to prove. So this statement is actually true. The dimension of infinite product of fields is a field with itself is 0. And this is not about the field with itself. You can take any field and try this and it will still be true. So product of infinite fields, field may be same, may be different. All of them will have dimension to be 0. So these are some zero dimension rings. Okay, so you can see this and keep in the mind, these are the zero dimension rings. Uh, so any doubts here about how the product worked and so on? Okay, so if you have any doubt, please let me know. Otherwise, I will move to next here. Okay. So let us move to now the next question. This true or false, that let R be a finite dimensional K algebra. When I say finite dimensional K algebra, so we know finite K algebra, finite type K algebra, and now this is finite K algebra. So this finite dimensional K algebra means that its rank as a K vector space is finite. So this finite dimensional and finite K algebra is kind of same. Okay, so R be a finite dimensional K algebra. So finite K algebra means I again informed this, mentioned this last time, that when we say finite K algebra, it means we are looking at that K algebra as a K module. And when I say finite type K algebra, it means it is finitely generated as a algebra. And that's the difference. And here they are saying it is finite dimensional K algebra. That is, it is finite dimensional module over K. That is, it is finite dimensional K vector space, because K is a field in our case. and that they are saying that rank is finite, that then we have to prove that, or then we have to check whether this R is Noetherian or not. So any guesses here? Whether this will be true, that we are given that R is finite dimensional K algebra, that is R has a finite rank over field K as a vector space. Then we have to check whether R is Artinian or not. So first thing to check that this R is Noetherian as well. Okay, so R is a Noetherian at least. How? Because see, this R is finite dimensional K algebra. So since R is finite dimensional K algebra, it means R is finite K algebra. Finite K algebra means it is finite as a K module. It is finitely generated K module, and this definitely implies. So when I say something is a finite as a K module, it is stronger than saying that it is finite as a K algebra. Okay, because when we say module, we have this linear combinations of the generating set. But when I say something is a finitely generated as a K algebra, we have polynomial combination of that generating set. So when we say something, so the linear combination is kind of anyway available in algebraic combination. I mean polynomial combination. So that's why when we say something is finite K algebra or finitely generated as a K module, it is stronger than saying that something is finite type K algebra or finitely generated K algebra. Okay, so once I have finite type K algebra, then by Hilbert basis theorem, we have that this R is Noetherian. Because K is a field, so K is Noetherian, and this R is finite K algebra, means R is a finitely generated as, I mean, R is a R is isomorphic to polynomial in finite variables over K. So it is a Noetherian. Therefore, R is Noetherian. I hope this is clear why this is Noetherian. So, and we have this result that if R is Artinian, then R is Noetherian and dimension of R is 0. So can we prove that dimension of R is 0? How to show that? So do you know any criteria which is equivalent to saying that if dimension of ring is a 0? We just had an example. This is the ring with dimension 0. And what we saw here, that this is prime ideal and this is also maximal ideal, because no other ideal contain no other proper ideal contains this uh, ideal in this 0 dimension ring. Okay, so so this is that dimension of R is 0 if and only if we know, or we can check, if and only if every prime ideal is maximal ideal. So how to start with this, that every prime ideal is a maximal ideal actually. So take, so we have to prove dimension R is 0. So suppose dimension of this R is greater than equal to 1 at least. Okay, so once I have this, then there exists some P in spec of R such that this P is not in M spec of R. We can always have this. Once I have chain of length 1, so I have some prime ideal here. So I have chain of this kind. Okay, so I'm choosing this prime ideal. Okay, so these kind of prime ideals are there. So I'm choosing this prime ideal such that it is in spec R and this is in. And note that this is the only, we can have this and so on. But at least we will have some ideal here which is maximal, which contains this P naught. And which is at least one prime ideal which is not in maximal ideal, because we will have chain of length 2 which contains this prime ideal and so on. So we can always have such kind of prime ideal, and then we quotient it. Okay, so then dimension of R mod P will also be greater than 0, because P is a prime ideal and it is still an integral domain. So its dimension uh, will still be some non-zero number, and therefore this R mod P is also a finitely generated K-algebra, because we are quotienting it with some ideal. So once we have finitely generated K-algebra, its quotient also is a finitely generated K-algebra. Okay, so therefore by Noether normalization lemma, I have finitely generated K-algebra. So there exist T1 to TD algebraically independent in RP such that R mod P is finite over this K T1 to TD. Okay, and this D is actually this dimension of R mod P over R and so on. Sorry, K. This ring R mod P. So therefore this D is actually this dimension of R mod P, and we know once I have Noether normalization, it is finite over, so finite over K. So the dimension is the same. So we are taking, this is the result. So this is Noether normalization. R is finite of R over RP and so on. So this R mod P contained in R, and this R K is here, and this T1 to DD, I'm just writing it in the form of Noether normalization. Okay, so therefore, but once, so this means that this KT is contained in R mod P because it is K algebra. So, and we are assuming its dimension is strictly greater than 0. So KT is at least contained in it, because K is a field and dimension is greater than 1, so there exists some variable here such that it is contained in this R mod P, and then this rank of R mod P is greater than this rank of this KT, because KT is just contained in this, and this projection from R to R mod P is on 2. Therefore, dimension of R is greater than equal to dimension of R mod P. So I have this KT contained in this R mod P. So dimension of this R mod P will be greater than this R mod K. So ontoness will actually give me this. So, but this is infinite. We know the dimension over K, okay, over K. This is infinite. But dimension of this is finite. So because we are already have this, because R is finitely generated algebra, and R mod P will also be finitely generated, but finitely generated as a finite dimensional vector space we are already given, but this is infinite. So which is contradiction, right? I mean, rank of this finite is greater than equal to rank of this infinite ring. So in general, what we have, this rank K over R greater than equal to this rank K R mod P greater than equal to rank of this K KT. And here everything is infinite. Not everything, I mean rank is infinite. But here the rank is finite, and even here. So that's the contradiction. And actually we don't even need to quotient it by P, and we can actually directly work with R. So K here K to R, we can just take this K to R, and we can work with it as well, because R itself is also a finite dimensional K algebra, and it is finitely generated as an algebra over K as well. So that's why this, therefore, this rank which we started with, sorry, dimension of R greater than equal to 0 is wrong. The assumption therefore dimension of R is 0. Okay, this finitely generated K algebra, or this finite dimensional K algebra, is actually playing a role here. So is it clear? I mean, we just want to have, we have to show that the dimension is 0. We cannot have this chain-like structure, because once we go modulo that, and this has one non-zero, so this P1 is here. Okay, so this P1 was here. So this P0 is getting 0 here, and this P1 quotiented by this P will still, and this will be prime because we are quotienting by this. So dimension of this R mod P is still some non-zero number. So we start with R greater than equal to 1, which was positive. So we had such chain. And now we are going modulo P, which is integral domain. We are going modulo P. So this is the integral domain. So this 0 ideal in this R mod P is prime ideal. And this P1 quotiented by P and so on, these are still prime ideals containing this P. So we still have this chain intact. And that's why the dimension will carry forward. Is that okay? So therefore, dimension of this R mod P is also positive. And once I have this dimension of R mod P greater than 0, through Northern normalization lemma, we get these extra variables such that this K over R mod P over R. So R mod P, R is finite over this K, T1, T2, TD. I think it won't be K, it will be this. Yeah, I think it will be here R mod P. Yeah, we are taking this T1, T2, TD in here. Okay, and this has dimension. So this is contained in my R. And you can see this. How? I hope this is clear. I mean, we are just saying that if I assume the dimension to be greater than 1, we will arrive at a contradiction using Northern normalization, because we will have that some variable which will be generated as a which will be contained in R as a algebra in one variable which has dimension at least 1, and that will give me the contradiction. I mean, I hope you understand what this means. Is it clear? I mean, at least you got the idea, right? I mean, what I'm trying to do here. We are reducing the dimension and arriving at the contradiction here. Okay. So we will move to now next question. This question 4, that let R be a Z graded ring. Consider the set R in R such that R is a homogeneous and degree of R is greater than equal to 0. Then true or false that S is subring of R. Okay, so we are given that R is this Z graded, I in Z, Ri. So what does graded module means? That I hope, let me just quickly recall what is graded module. So let R be a Artinian local ring and S be this R algebra x1 to xn with degree of xi 1 is said to be 1 for all I. Then this gives the decomposition of S as S is equal to I in N or Z, doesn't matter. Let me write just Z as R modules. Okay, and where Si are R modules which are free and generated by monomials. This x1 power a1, xn power an, such that the summation ai is I. So this much is clear, right? I mean, this is given in the note. And this Si is a graded ring. Sorry, this S is graded ring if Si Sj is contained in Si plus Sj for all I plus j. So something being graded module means we have this gradation. We can write it as direct sum. such that each component contains only the degree elements of that component. And we say that S is a graded ring if this Si into Sj. So we are in the ring, so a product is possible. This Si and Sj are, we can look, since Si and Si is module, so Si is ideal in this ring S, and similarly Sj is an ideal this ring S. So Si into Sj must be, must be this component Si plus J. Okay. So this is like in polynomial ring, the of Kx. So Kx can be written as I in Z. What I have this. Let me write this Ri, where Ri is x power I, not ideal, but R x power I plus R. Okay, we are in only one variable. So let me check this. At least this x power I plus R, and this y is 0, x I minus 1, y I, y1, and so on. R x, not x, only y power I, and so on. So I mean, it contains the degree I component as a summand. Finitely generated as a vector space over, sorry, module as a over itself, over K here actually. And we get this. And when we say that S and S module, M is said to be a graded S module if M has decomposition, again M has decomposition, and such that M is this, and such that this Si into Mj is contained in Mi plus J. So Si is a graded component in my, so S is this and M is this here. So when I multiply the ith component with the jth component of Mj, so this is some element in M, and all those elements of this form, such that Si into Mj, they should land in my pre-module Mi plus J. I'm the degree I plus jth component of this decomposition. Okay, and this should happen for all ij. And for all I, so for each this I, so this I is in Z, so for or any index set over which we are taking the decomposition, the elements of Si or this Mi. So when I'm talking about ring, this Si, and when I'm talking about graded module, this Mi, are called the homogeneous component of degree I. So each this Mi is a homogeneous component. It is called as homogeneous component of degree I. And here in our question, they are considering R to be a Z graded ring. And they are considering this set S is R in R, such that R is homogeneous and degree of R is greater than equal to 0. Not, not greater than equal, greater than 0. Then we have to show that S is a subring of R. I mean, is this true or not? So when I say S is a subring of R, it means it should be closed under addition, multiplication, and it should also contain the one, I mean the multiplicative identity of the ring. Can you yeah, we want 1. So this is greater than equal to. So can you guess whether this is true or false? Anything? So this is false, right? Because what the set S is, it is R in R such that R is a homogeneous component. And degree of R is greater than equal to 0. So suppose I take some element R1 in R with degree, let us say I1, degree of R1 is equal to I1. And if I take R2 with degree R2 is equal to I2 and I1 not equal to I2. If I take this, then this element R1 plus R2, is this in this ring S? So S contains all homogeneous ideals. So when I say something is a homogeneous, it is element of this homogeneous component. So do you know which homogeneous component this R1 plus R2 belong? Or does not exist any component where this R1 plus R2 belongs? So it does not belong to any components. This is not homogeneous component. Sorry, this is not homogeneous element in R. Therefore, R1 plus R2 does not contain in S. So this S is not even what I can say. This S does not even contain is not under the addition. Okay, so therefore S is not subring. So when can we say that something is a subring? So what changes would you like to make such that if S can become a subring of R? Any suggestions? When can we say that this S is subring of R? I mean, can we, so homogeneity is okay. So what changes would you like to make on the second component such that we can have this degree R to be greater than equal, sorry, this S to be subring of R? Almost degree? Uh, uh, Almost degree means, okay, so you are saying that at least one of the, I mean, we have to take maximum of the degrees or something. I don't. So the only possibility is because, see, we consider one to be of degree because, see, when we multiply one by some component R, it is again R. So one must be in S0. For something to be a subring, we want at least one belong to that set. Okay, so this S is equal to R in R such that, so this is just to get an idea like what degree to choose such that R is homogeneous and degree of R is equal to 0. Okay, but still this is just a collection of homogeneous element such that degree R is 0. So, but can we prove that one actually belongs here? Let's Okay, so in this case, for so in this case, see, because if our degree in the R1 plus R2, degree of R1 plus R2 will be degree 0 again, will be 0, and degree of R1 into R2 is equal to degree of R1 into degree of R2. We are in integral domain, so nothing is going to 0. So not about integral domain, but yeah, I mean, this degree of R1 plus R2 will be degree of R1 plus R2, which is 0 plus 0, so 0. So note that here, if we had taken any non, I mean, element R, or here, if I had taken some non-zero element or non-zero degree n, that in that case, this product would land in n plus n or 2n component. Okay, this product. So this will not be my ring, subring, because product must be closed. Okay, so this will not happen. That's why we need this to be 0, the degree R to be 0. And now our aim is to show that to show that one actually belongs to this S. Can you, first of all, do you understand that we actually need to prove that one is here? Because one could be, so it is just collection of homogeneous elements such a degree R is 0. So, but we need to actually show that this set actually contains 0, because we can't directly say it from here. So how to do that is to show that is my R0 actually. So this is R0 component. So how to do that? So since one is in S, one is sorry, not this sum, this summation I from 0 to M. Okay, this EI belongs to Ri and I is in Z. We are taking Z gradation of S. Then for all EJs, this EJ into 1 is equal to summation I from 0 to M EJ into EI. So this implies this EJ into summation I from 0 to M EI EJ. Okay, and now degree of this EI into EJ is I plus J. Okay, and so here this is degree J element, degree of EJ is here, let me show you. Yeah, when I say this, it means degree of EI is Ri. So degree of EJ is J. And here I am getting degree of this each element EI EJ to be I plus J. Okay, so therefore, to at least match the degree, we must have this EJ to be E naught EJ, right? Because all other elements will increase the degree. So we will have degree of this EJ to be J and degree on the right hand side to be some M plus J or whatever. But so, I mean, it will increase by some number if we have any non-zero degree term involved in this expression. I hope you understand that. And if not, please let me know. So this is true for all EJs, right? This is true for all EJs. Okay. So this implies this E naught is E naught into 1 into E naught, which is again E naught into summation I from 1 to M EI, which is summation I from 1 to M E naught EI. But this was the expression of this. Each EJ is E naught EJ. So this is just summation I from 0 to M EI. And which was my 1. So E naught is actually 1. Okay, so therefore in 1 belongs to this S. We needed to prove this. Okay, just because we have 0 degree terms. So this explicitly also proves that element 1 actually has degree 0. Okay, we started with the just a set containing homogeneous element of degree 0, but we want to prove that it is a subring. So we started, so addition is there, I mean the degree of same homogeneous component. If we add two elements from same homogeneous component, they will be in again the same homogeneous component. So again the product here satisfies this degree condition, because degree of R1 and R2 both was 0, and degree of R1 into R2 will be the degree of R1 plus R2, and which is again a 0 because we are in degree 0 component. But now to prove that it is a subring, we need to show that 1 belongs there. And we only have the information about R being homogeneous, and degree of elements of this R is 0. So that's why we started with this. So we have to show that this 1 belongs to this R naught. So if 1 is a sum, if 1 does not contain in any of this, if it is not in this 0th component, it will be summation of some this E1 to EM. Okay, this, when I write this, I'm just saying that 1 need not be homogeneous element. It is just expression or addition of some homogeneous components. In general, element look like this. I'm not even assuming that this 1 is a homogeneous element. I'm just starting with the 1. 1 is a summation of some homogeneous component, and we actually arrived at the conclusion that this 1 is some element in the 0 degree component, and that's why this 1 belongs to my multiplicative set S. I hope the logic is clear, like why we needed to prove this, that 1 is in this set. If not, please let me know that why we have to prove this 1 belong in that set. Okay, if not, then I hope this is clear. So let us move to next question. Again, this is true or false. The Hilbert polynomial of this k x comma y is P2. And what is this P2? So we have this, that we define this polynomials Pk, which is not actually x choose k, but it has this short form, and it actually represents this polynomial x into x minus 1, x minus k plus 1 divided by k factorial. And this is some polynomial in Qx. Okay, the coefficients are from Q because of this k factorial, and all the other, these are only x minus I kind of, where I is some integer. So the numerator is in zx, but once we divide it by this k factorial, we are in the polynomials over rational coefficients. So just then P0 will be my 1. Sorry, P1 will be what? Just this x. And P2 will be this x into x minus 1 by 2 factorial, which is x square by 2 minus x by 2, and so on. So PIs are of this form. So what is Hilbert function? So we are asked, so what is Hilbert polynomial? So to understand Hilbert polynomial, we actually need to know what is Hilbert function. Okay, so let us understand that first. What is Hilbert function? That let R be a Artinian local ring. S is R kx1 to xn, and degree of this xi is 1 for all I. Again, we are in same setup as earlier. And then M is finitely generated. R module. And then M is this J in Z, R modules. So M is this direct sum, and we know that this each Mj is finitely generated R module. Okay. So M, we are starting with the finitely generated R module, and then again I'm expressing M as a decomposition, and I'm again saying that this each of this Mj is finitely generated. Okay, it's finitely it's not Mj is finite, has a finite length as an R module. And what is this? So I will tell you what this length means. So the function hm from z to z. So I'm assuming that Mj has a finite length. So that's exactly what I define here. Lambda r Mj. So the J is going to this lambda r Mj. And in this decomposition, when we have this J to be zero ideal, then this lambda r 0 is just number 0. And this Hm is called Hilbert function of M. Okay, because here this Mj is of this. So this is Hilbert function for this M. And we are here again over the decomposition is over Z. That's why this is well defined. Okay. And further we have this, that there exists a PM in QX. So again, a polynomial in my polynomial ring over rational coefficient, such that for all J big enough, this PMJ is HMJ. Is that okay? So when I say that J big enough, so for initial elements of J or the smaller elements of J, this need not hold. But there exists some big enough J such that this PM of J is HM of J. Okay. And this PM now then called as Hilbert polynomial of M. Is this okay? This polynomial PM is called as Hilbert polynomial of M. Any doubt in the definition? I hope this is clear. And the length, so length here I have written. So length is actually the, what I would say, it is the length of a composition series. I hope you know the definition of composition series. Uh, is it, do you know that, right? So, so every module has the composition series of a descending filtration. So if M is R module, then the composition series of M is just descending of descending filtration. So it starts with M, and M contains this M1, which is a submodule of my M, again contained in M2, and so on. And there exists some MR such that it becomes a 0. Okay, so such that this Mi minus 1 quotiented by Mi is a simple R module. So when I say simple R module, it is module, it is R mod M module also for some maximal ideal. So, I mean, you can go through a definition. I am not spending much time. And the chain which I have here, that the length of that chain is called as, the length of that filtration is actually called as length of my module M. So here when I write this, it is held length of this each Mj. So Mj has, so Mj is finitely generated. It's a finite length R module. So this M1 to Mr has filtration. Mj has this filtration. Mj is equal to Mj0, Mj1, Mj2, and so on. Since it is finite length, there will exist some. Okay, so and if this Mjr, if it doesn't become 0 in the composition series, then we consider this lambda r to be infinite. Okay, from the notation, and this r here is actually my lambda mr. So I hope this much is clear. So we have this, right? So R is my kxy. So how to write this? So R, if I try to write the filtration of R, it is k plus this kx. So when I write this, there as a modules, plus this kx square plus kxy plus ky square, direct sum, and so on. It continues with all the degrees. Okay, so if I call this R0, R1, this R2, such that this Ri is collection of homogeneous polynomials of degree D. Okay, and how many such generators are possible? Okay, so when I try to write, what I can say, length of this polynomial, uh, this each component Mj, it is this, right? What I can say, so my R1 is this kx plus ky, which is properly contains kx, and now this properly contains 0. So that's it. This is the only possible composition of this K module. Okay. So how to find this length? We need to have length to, so my Hilbert polynomial is such that it is Pmj is equal to Hmj for some maximum M possible. So can you find this? So this length of Ri is actually this n plus d minus 1 n minus 1. So therefore this lambda r, oh sorry, d is just this d plus 1 by 1, which is actually p1. Okay, because here the elements are of this form, right? Xi in d, and it has only d plus 1 possibilities. So this is d plus 1. I hope this is clear. So therefore, and this is p1. Okay, this is my p1 from here. I want a j maximum such that this h. So I want to find the dimension of this R module in short. I want to find dimension of this R module, each Ri or Rd. I want to find each length of this Rd. So because how it will happen? I have this Rd. So explicitly for this example, x square plus kxy plus ky square, right? This will be my m0. This will be contained in, you can omit one of the component and it still works, a kxy, right? And this will be contained in this kx square, which will be 0. I mean, that's what we need here, right? To have the definition. Let me just check the definition once. Yes, this mr to be 0. So this is my mr. So m0, m1, m2, m3. Okay. So our dimension of R2 is 3. I mean, we can't go further. If it is finitely generated by, so in short, this 3 is what? 3 is generator, number of generators of this R2. So in general, and that is in fact my lambda k R2. Is it okay? So I want to find this lambda k R2 and what it will be? It will be d plus 1, right? And why it will be d plus 1? Because what are the generators here as a module? If I look at it, it is all the elements of the form x power I, y power d minus I, right? Because for certain d, it will be kx power d. I mean, I can take this d minus I and I, it doesn't matter. Plus this k x power d minus 1, y, so on, up to x d kx d, not what, kxy d minus 1 plus ky power d. And these are d plus 1 elements because at each position I'm reducing 1d and here it is d plus 1 term. So this lambda 2 of rd is actually, lambda k over rd is actually d plus 1. So it is like we are finding dimension of this module rd over k. Is this okay now? So therefore this, what I was saying? Yes, so this lambda is lambda k rd and therefore this is p1. Okay. And here we want, there exists some pm in qx such that pmj is equal to hmj. Okay, for j big enough. So that is satisfied. So therefore Hilbert. So my Hilbert series looks like this. Hilbert function looks like this. Hm. Z to Z. Zeroth component has 1. So here 2 has 3. So n goes to n plus 1. Okay, and for j big enough, I want PMJ is equal to HMJ. So what was my P1? P1 was my X. And I mean, P1 was, there exists PM in QX such that, so degree 1, I mean, so this is equivalent to, so this is my P1, okay? I mean, we can check this in Macaulay too. And in fact, for n variables, let me write this. For n variables, this kx1 to xn has Hilbert polynomial Pn minus 1. Okay, so let me just share the screen to show you. I hope this screen is visible. So we want to check the Hilbert polynomial of ring x comma y. I hope it's load this. R is equal to QQ comma y. So this is, I'm taking a polynomial ring and just oops, I'm not sharing. So I hope this is clear. So I have defined this ring in two variables. R is equal to QQ comma y. And now I want to find the Hilbert polynomial. So it is, the code is just this Hilbert polynomial of R. And it is just giving me this projective Hilbert polynomial P1. P1 is what we defined earlier in our notes, that PK, the x minus, the PK was x minus x into x minus 1 up to x minus k plus 1 divided by k factorial. So that is this polynomial P1. And you can check. So since I said that if I take x1 to x7, for example, so it is just, since I used earlier variable x, this is giving me information that they got rid of that variable x, and I'm now having this new polynomial ring and so on. That's not, I mean, that's okay. But now when I check this, so for 7 variables, I have this P6. Okay, so for any k variable terms, my Hilbert polynomial is Pn minus 1. And you can check that. Because again, there also, when the degree changes, since we have k variables, we have these possibilities of choosing the powers of variable. And that is exactly that n choose k for that particular degree n term and so on. So I hope you can understand that why this is happening and how this coincides with the our initial polynomial which we defined, this projective Hilbert polynomial, or those pKs which we defined uh, earlier of this question. And you can also find, so since we are here, so we can also define this Hilbert polynomial for quotient rings as well. So let me just take this x1. I hope it works. And we are just doing Hilbert polynomial of this R mod I, and it is some different polynomial. It is minus p3 plus 2p4. So it is minus of p3 plus 2p4, but it is still a polynomial in degree 3. So we can have such polynomials for rings, quotient rings, and also for ideals. So I can just write Hilbert polynomial of ideal, and it gives the same, because when I did this, when I write this Hilbert polynomial of I, it considers it as a R module and works. Okay, so we can do this Hilbert polynomial ring for ring, quotient ring, and also we can do it for module. Okay, so I can just write T is equal to module R. Then again, I'm just writing this Hilbert polynomial of T is again this, because R was my 6 variable term, and again this T is also the same thing. So we can define or calculate Hilbert polynomial in Macaulay 2 for rings, modules, quotient rings, and ideals. I hope this is clear for now. Okay, so if you are okay, then we'll move back to again the previous question which we were working on. So before I stop sharing, please understand that this Hilbert polynomial of RQXY is this P1 which we had. So is that clear? Okay, so I'm moving to now next question if we have time. So question 6, that let M1 is equal to Kx quotiented by ideal x, direct sum x quotiented by x square. Okay, so and M2 is equal to Kx quotiented by x square and the Kx modules. Okay, so I have these two modules here, and true or false that M1 comma M2 has same Hilbert function but is not isomorphic, but but not isomorphic, but M1 and M2 are not isomorphic. Is this okay? Can you understand the question? So we are given these two modules and they are Kx modules. So we have to check that they have same Hilbert polynomial, but they are not isomorphic. So whether this is true or not. So can you at least see that why these two modules are not isomorphic? Know that M1, M2 is cyclic. This M2 is generated by 1 bar in Kx over x square over Kx. Is this clear? The one generates this entire module M2. Is that okay? The one generates the whole ring over itself as a module. Is that okay? So similarly, this M2 is a quotient ring, and this 1 bar in this ring actually generate this uh, module M2 as a Kx module. But this M1, so this is cyclic. This is cyclic. Cyclic means generated by one element. Okay, but this M1 is what? It is direct sum of these two modules. So once we have direct sum, it won't be generated by, it won't be cyclic, right? Because if I choose some element a comma b here, then it will be generated by that a comma b. So this M1 is not generated because this each kx comma x, sorry, quotiented by x, this is generated by 1 bar, similar to M2, and this x square, sorry, this x mod x square is generated by this x bar. So this is cyclic, okay, and non-zero cyclic. So this can never be isomorphic to cyclic module. Okay, so the direct sum of cyclic need not be, I mean, it's not cyclic in general. So that's why M1 is clearly not isomorphic to M2 because M2 is acyclic, but M1 is not cyclic. Is that okay that these two are not isomorphic modules? Is that clear at least? I hope it is clear. If not, please let me know. Uh, Now we have to find the Hilbert polynomial for both of them. So at least this part is okay that M1 and M2 are not isomorphic. But we have to check whether they have same Hilbert polynomial or not. So, okay. So before going to x square, let us work with this because it is similar. Kx quotiented by x. Okay. When I say as kx module. Okay, so the kx is generated by 1 as kx module, right? Because every element a in kx, what can be written as a into 1. Okay, so this 1 becomes the generator of kx over itself. And again, this in this quotient ring, as again kx module. Okay, so every element in kx is of what form? M plus this ideal generated by x. So this f is, so I can write it as 1 bar plus x into f, where f belong to kx. 1 bar, not 1 bar, 1. I mean, that's how module multiplication works here, right? The quotient over as a kx module. So therefore, this 1 plus, then this is for all f plus x in here. So this 1 plus x is generator as kx module of kx mod x as kx module. Is this okay? So therefore, this 1 plus x is what? This is just 1 bar, the multiplicative identity in this kx, k quotiented by x. Is this okay now? Okay, so this 1 bars are actually generating these cyclic modules here. Okay, so I hope that was clear. So let me move to next question then. Not next question, yeah, the next part. We are not yet done with this. We have to show that Hilbert polynomial of this both the rings, sorry, this both the modules is the same. So how to show that? So let us start with M2 first, because M2 is better looking than M1, because here we have direct sums, but here we just have one quotient. So M2 is what? M2 is kx quotiented by x square. So how the elements here look like? A plus, I mean, polynomial here in general is a0 plus a1x plus a2x square and so on, right? Plus an x power n. But everything from, I mean, the degree 2, the terms of degree 2 or bigger are going to 0. Are going to 0 means are getting vanished because of because we are quotienting by s square. They are becoming 0 in the quotient ring. So the only part which survives of any polynomial is this a0 plus a1x in the quotient, okay? In quotient. So this M2 has this form, b into this x bar, such that x bar is that x into x square in my quotient ring, such that a comma b is in k here. Is this okay? Like how this M2 is actually this set? 1 is this 1 plus 0 x bar. 0 is 0 plus 0 x bar. So this is the entire ring. How, I mean, I hope this is clear to you. And so this, when I write this, so I can write this M2 to be this k plus kx bar, right? This is degree 0 term and this is degree 1. So this m is actually direct sum of this, because every element of it looks like this. Is there doubt here? So therefore, this length of M2 of degree 0, I mean, this is degree 0, right? It is 1. Only one element is available. And similarly, for first degree component, it is 1. So Hilbert polynomial is 1 at this 0 and first, I mean, and for all, let me take r not equal to 0, r 0 comma 1. This lambda m2r is 0. All other components are 0, because my M2 is entirely this k direct sum kx bar. Is this okay? So therefore, this is my Hilbert function. Hilbert function, right? We have to check the Hilbert function. Yeah, Hilbert function. Okay, so Hilbert function is this. At 1, 0 and 1, it is 1, 1, rest is 0. Now we have to check that for this M1. M1 is what? This Ka quotiented by x, right? Direct sum x quotiented by x square. So kx quotiented by x contains what? Kx quotiented by x. It only contains these constants, right? I hope this is clear to you that it only contains constants. Because any polynomial of this form, a0 plus a1x and so on, x onwards everything vanishes, similar to what we had here. X square onward everything vanished in quotient. So this is generated by 1 bar here. And this is ideal generated by x in quotient ring. So That's not a problem because again ideal generated by x here are what? It is x into some fx. Okay, so once I have this, so whatever the polynomial be, so x into, which is x into, let me write, a naught plus a1x plus so on, then it will be a naught x plus a1x square plus, but again I'm quotienting by x square. So everything from here onwards vanishes. And this second component, x mod x square, it is also now generated by these elements of this form, a naught x, such that again, let me write only a x, such that x belongs to, sorry, a belongs to k. Is this okay? So therefore this m1 is what? This is this, how to write this? Yeah. So this is my this k plus k x bar, because this is anyway k. This is only kx bar if I look at it. So this is degree 1, degree 0 term. This is again degree 1 term. Therefore, my lambda m10 is again 1. Lambda m11 is 1, and this lambda m1r is 0 for r not in 0, 1. Okay, so they have same Hilbert polynomial, right? 1, 1, and similarly 1, 1 and 0 for rest of the terms. So that's why these two modules have same Hilbert polynomial, but they are not isomorphic as modules. Is this clear? I mean, it was just to understand that how these modules are generated. That was the only work which we had to do here. And once we know how modules are generated, we just have to find like the number of generators in each component or each degree component, and then we get the Hilbert polynomial. I hope this is okay. So last quick question. We have some time. Okay, clear. Great. So we'll move to this next question, that is this x square y cube is a system of system of parametrization of kx comma y quotiented by x comma y. Again, we are in this ring, polynomial ring, and we have to find whether it is system of parameterization. So system of parameterization, let me give a quick definition, that R comma M be a local Noetherian ring and M is finitely generated R module, or let me write here, M is finitely generated R module. Then dimension of M is D and x1 to xd are in M. Now that x1 to xd are in this maximal ideal, this unique maximal ideal of this local ring. These elements x1 to xd are called system of parametrization if dimension of this M quotiented by this x1 to xd M is a 0. So I have to find that. So what exactly, so when I want to check whether this x square minus y cube, when I write this, I mean, yeah, is a system of parametrization. What I need to check is that whether this M quotient, this, what is my ring? Let me give this ring a name R. Okay. So I need to check whether this R into ideal generated by this has dimension to check whether dimension is 0 or not, right? I mean, that's what we need to check. But what is dimension of this ring, this kx comma y quotiented by this, what was it? I think xy quotiented by this x square minus y cube. I mean, quotiented by x square minus y cube comma xy. Sorry, not this. I mean, okay, this is isomorphic to my, this is my actual ring. This is, I mean, this is what I need to check, dimension of this. And this is isomorphic to kx comma y quotiented by x square minus y cube comma xy. This is what I need to check, the dimension of whether dimension of this ring is 0 or not. So note that dimension of this ring kx comma y, even for polynomial ring, sorry, formal power series ring, it is 2 because we have this. Okay. Again, this is also a local ring with only this as maximal ideal, because similar to power series ring in one variable, the once we have non-zero coefficient, since again we are in field, the once we have non-zero constant term in a polynomial of a formal power series ring over a field, it becomes a unit. So if I have, if at all, if I have any ideal which which is proper in this power series ring, again it has to be generated by some power of x and y, x and y, x or y, or the polynomial or the product of those two. In either case, in both the cases, the it will be contained in this maximal ideal x comma y. So that is the only maximal ideal we have again in this formal power series ring. So now again this xy also, this xy is non-zero divisor in k x comma y. Then this dimension of k x comma y quotiented by this will be 1. So whenever we take quotient with respect to any non-zero divisor, the going modulo that element reduces the dimension. Okay, so I need to now show that dimension of this x square minus y cube comma xy is 0. So that is every maximal ideal is prime, right? Sorry, every prime ideal is maximal. Okay. And how to show that? So let P be in spec k x comma y. Then, no, not this. Let me call this ring R. Spec R. This implies this x square minus y cube comma xy is contained in this prime P, right? And once I have this, it means xy belongs to P. This implies, then since this is prime ideal, x belongs to P and y belongs to P. And the moment I have x in P and I have this x square minus y cube in P, it implies that y cube is in P, right? Because x is in P, x square is in P. Once I have x square in P, x square minus y cube is in P. So I subtract, add them such that I get y cube. And the moment I have this, I get y in P. So therefore, this prime ideal P becomes this x comma y. And similarly here, Once I have y, this will imply my x square belong to P. Similar argument, again x belongs to P, and this imply my P is this x comma y. So we started with some prime ideal and we ended up getting that P is exactly the maximal ideal x comma y. So therefore, every prime ideal is, let me write, every prime ideal is maximal in R. Therefore, therefore x square minus y cube is system of parameter of this power series ring. Okay, we are in power series ring quotiented by xy. Any doubts here? Like how we are doing this? So we are heavy, I mean, we are only using this fact. I mean, we didn't even need to know what dimension of this or what dimension of this is. We don't even care that. We just wanted to check whether dimension of this is zero or not. Okay, we don't need this. Let me write here. We actually need not know, do not need to know the dimension of this or know these dimensions. Okay, only need to we only care about the dimension of this. Once I have dimension of this to be zero, I can say that this x square minus y cube comma xy is system of parameter. I mean, this x square minus y cube is a system of parameter of k x comma y quotiented by ideal generated by xy. Is this clear? I mean, we just had to find and we started from here. We want to actually find this. We started from here and we proved, not proved, we showed that these two are actually isomorphic. So that's why we found the, what I can say, dimension of this ring instead of this ring which we started with. Instead of finding this dimension of this ring, we found the dimension of this ring because anyway these two are isomorphic. Okay, so it's over 5, I guess. So I think we can stop here for today. Is there any doubt in what we did today or anything from the lecture? Please let me know, or anything. If any doubts? I think, okay, solution of assignments. You didn't receive it for earlier weeks? If you are not receiving it, please write it in the discussion forum that you would like to have the solution set for the assignments, and maybe NPTEL can provide it to you. Not received it for a single week. Okay, so you can email in the discussion forum that you would like to have the solution for this assignments, and then they might try to upload it if possible. Okay, and I hope this was okay for this session. If you have any doubts, please post it in the discussion forum. Okay, thank you.